Chapter 4, we're going to talk about chemical bonding. What constitutes a chemical bond and how do we use it to describe chemical changes? Yep. That's good. All right. As a general outline, we'll get to those eventually. So a generalized description of a chemical bond is the force that holds two atoms together. That's as simple as you can get. Now, it can hold them together into a complex unit that is an array of, it's just as big as you want it to be, of positive and negatively charged ions, cations and anions. Those are ionic compounds. Or you can get atoms held together so that they behave as a single unit. Right? Those are the ones that, example like water. Now, when two atoms come together and they're going to form a bond, maybe, what do they see first as they approach? That's not a trick question. They see electrons, right? The nuclei don't get anywhere near each other. So the bonding is a result of interactions between electrons of the combining atoms. Now we can subdivide those into the first type I described as an array of positive and negative charges. Those are ionic bonds that form. And ionic bonds are the easiest to understand because they're purely electrostatic. You know, negative attracts positive. It's just that simple. Covalent bonds are a little more difficult to describe because they involve sharing electrons. Now, ionic bonds form between metals, right? You know the periodic table. Metals are on the left, nonmetals are on the right. So between metals and nonmetals, you get ionic bonds as a broad category. Covalent bonds occur between nonmetals and nonmetals. So those elements on the right-hand side can form bonds, but the attractiveness, the attraction of electrons of one versus the other are not exactly evenly matched, but more closely matched so that electrons aren't given up by one to the other one. That's what forms ions. So they compromise, they share electrons. Now we didn't always believe some of these things that you're going to study in the next two or three chapters. It's like, I'm pretty sure I've described before, most scientists make careers out of tearing things apart and seeing what they're made of, or describing details. Every once in a while, you get a mind comes along that synthesizes all that information into a coherent description, a theory maybe. And one of those is Linus Pauling. So he researched the nature of the chemical bond, and he published a book by that name. And it solved so many problems and was used by so many scientists to solve other problems that the Nobel Prize Committee thought he was worthy of a Nobel Prize in Chemistry in 1954. He was also famous for mega doses of vitamin C. And he wasn't really wrong about that. I mean, when I feel a cold coming on, I take 1,000 milligrams a day of vitamin C, and it shortens the duration. I know from past history, if I don't, it'll drag out. Anyway, so this ionic bond is the consequence of transfer of electrons. So, for example, if we have a neutral atom of sodium and a neutral atom of chlorine, metals like to give up electrons. And in fact, the alkaline metals like to give up one electron. That's it, just one electron. They'll be happy to give it up. Chlorine is a halogen on the far right side, and the halogens just love to accept one electron. So we get a transfer of one electron over here, and that makes, let's see, sodium is 11 protons, right? 11 protons, 11 electrons. So if we take one of these negatives and transfer it over there, we get a net positive charge, right? We have 11 positives and 10 negatives, which gives us plus one charge. Now, chlorine is 17, right? So it has 17 electrons. And if we add another electron to it, now it's got 18. So 17 positives and 18 negatives gives you a negative net charge. Okay? Once that transfer has taken place, then you get an electrostatic attraction between a positive and a negative. It's just that simple. Whereas covalent bonds form between two nonmetals. And we describe them that they all make compounds when you combine different elements. You get a compound. But there's a difference between ionic compounds like I just described and molecular compounds. Compounds that form discrete units, and these are always nonmetal, are molecular compounds because those molecules that they form act as independent players. Whereas if you have an ionic compound, you're going to have an array of positives and negatives. Something like this. This is only 2 dimensions, right? You have to think in 3 dimensions. There's chlorine behind and chlorine in front. And then you have sodium over here, and it just goes on and on and on, as big as the crystal. Right? You ever spill salt on the table and looked at it with a magnifying glass? Nobody does that anymore. What do you see? Well, if you try it at home, you'll see little cubes. That's an indication of the microscopic structure of the array of positives and negatives. Right? So in contrast, the covalent bond forms between 2 or more atoms and produces a discrete molecule that behaves independently. That's the way water molecules do. Carbon dioxide molecules do that. Let's see, other examples. Let's see. Oh, you can get some nasty ones like hydrogen fluoride. Or sulfur dioxide, drive through Greenbrier County and roll the window down, right? Some spots along there, you'll smell it, sulfur dioxide. So those molecules form bonds that by the sharing of electrons, and we'll get into more detail in a minute. Just those are the 2 distinctions. Now we have to remember, nature just does what it does. And what we're trying to do is categorize it and make sense of it. So if you have a purely ionic arrangement, that would be 100% ionic. Well, as a matter of fact, every bond has some ionic character and some covalent character, with very few exceptions. So there's going to be some sharing here, but mostly ionic. So you get a spectrum. Like if you have 100% ionic here and 100% covalent here, then all of the compounds are going to fall somewhere in between. Some of them will be on either end, but most of them will be here. In fact, you only get a purely covalent when you have exactly the same elements bound together. And when that happens, you don't have a compound anymore. You've got to have two or more different elements to have a compound. So our diatomic elements like hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, those are elements that are bound together by covalent bonds, pure covalent bonds, because they're exactly the same elements. Nobody wins. They have to share. So those examples are covalent, 100% covalent bonds. But if you get two different elements, more than likely, they're going to have slightly ionic character, at least. Okay, and another general rule is the closer the elements are together, each other from left and right, metal, non-metal, the more covalent character they'll have as they get closer together. The most ionic bonds are the ones that are furthest apart on the periodic table, like lower left, cesium and fluorine. Cesium fluoride will have the most ionic character that we can produce as a diatomic element. All right. To try to get a handle on things without getting too complicated, we've drawn a distinction between the electrons that actively participate in bonding and those that just generally mind their own business. The ones that are in the outermost shells, the valence electrons that we studied in a previous chapter, right? They all have the same principal quantum number. Those are valence electrons. Those are the ones that participate in bonding. The others are core electrons, right? And they generally don't participate in bonding. For example, if we say, let's see, carbon dioxide, how about that one? So carbon, we know, is 6 electrons, right? So it'd be a 1s2, a 2s2, and a 2p2. That oxygen would be, let's see, 8. Yeah, it has 8. So each oxygen would be like this. It'd be 1s2, 2s2, 2p4. These are the valence electrons for carbon. These are the valence electrons for oxygen. Okay, those are the ones that participate. And since carbon and oxygen are both nonmetals, they have to share. So, well, I don't want to get into that much detail yet. Let's just, let's go to the next point. And have any of you had anatomy and physiology or a biology class? So they give you a little bit of chemistry, a small dose of chemistry, and they may focus on the octet rule. So what elements are trying to do, especially in the second and third periods, those elements are pretty consistent with the octet rule. And the octet rule just says that the valence shell can hold 8 electrons, right? Because we can have 2 more here, and that would be 6 and 2 is 8. And we can have 4 more here, and that would be 8. So they're trying to fill this outermost shell, and that would be 8, because maximum 2 here and 6 there. So how do they do that? Well, if we have a carbon here with these 2, it can donate 2 to that 1 oxygen, right? Share 2 with that 1 oxygen. That would give it an octet. But there's another oxygen there. How does it do that? Well, okay, so how many does it need here? It gives you 4. So you could do either carbon monoxide or carbon dioxide, and I'm down a rabbit hole. I'm getting too complicated. Let's just leave it at octet rule. They try to, the bonds the sharing of electrons gives you an octet in your outermost shell. Let's leave it at that for now. Okay. Okay. Ionic bonds form a transfer of electrons from one atom to another. And the valence electron is the outermost shell electrons. And I've described that for you already. Those are the ones that participate. There's a point in there that's important. Why the octet rule? Notice that if we have, say, carbon or oxygen, and if carbon obtains 4 electrons, now it would have, theoretically, 2s2, 2p4. What does that look like? 4, 5, 6, 7, 8. That looks like, well, plus these two. Let's see. That's not right. That's 6, excuse me, 6. 8 plus 2 is 10. So that's neon. What they're trying to do is fill the outer shell so they look like a noble gas. That's one of the explanations for why the octet rule works. Because at least in the second period and the third period, obtaining an octet makes your electronic structure look like a noble gas. And we all know that noble gases are very stable. They don't react with anything. And they're trying for, during a chemical reaction, we're trying for the lowest energy possible. We're trying for stability. Or the players in the reaction are trying for stability. Now, of course, with hydrogen, it's trying to look like helium. So that's the duet rule. Hydrogen is special. Okay, one of the ways to visualize the octet rule and use it for chemical reactions, and this is where it'll work a whole lot better for carbon dioxide if we do it this way. Let's see, let's erase that. Is the Lewis symbol or the Lewis dot structure for elements. And what we do is G.N. Lewis was a brilliant chemist, an American. And he proposed just writing the symbol like carbon. And around that symbol, we would position the valence electrons. So the valence electrons for carbon, and you can tell how many valence electrons there are. Just see where carbon is, count from the left. Lithium, beryllium, boron, carbon. That's 4 positions. You have 4 valence electrons. And you position them. If there's only 4, then you position them as if they were lone electrons. Oxygen would have position that's 2 positions to the right. Instead of 4, it would have 6. So oxygen we would write like this. 1, 2, 3, 4, 5, 6, something like that. And that's a Lewis dot structure. And those are examples of other elements where we would use the Lewis dot structure. Notice all the alkali metals only have 1 electron in their valence shell. Alkaline earths have 2, boron, aluminum, 3, carbon, silicon, 4, nitrogens, 5, chalcogens, 6, halogens, 7. So how many do we need to complete the outer shell? In this one, we need 4 electrons. And here we need 2 electrons. Okay? And noble gases don't need any. Helium's got its duet, neon and argon have their octets already. Okay, so how about the number of valence electrons in each of the following elements? I'll leave that there. Calcium. The simplest way is to look, where is calcium on the periodic table? It's in the second column, right? It needs 2 valence electrons. That's it. And you can tell they're 4s2 because it's in the fourth period. And the first two columns on the left were filling s orbitals. So 4s2 would be perfect for calcium. How about selenium? Selenium is in the same period as calcium, but now we're into the p section. So selenium, selenium would be 1, 2, 3, 4, 5, 6 over. We skipped over the transition metals. So what did I say, 6? Yeah, 6. Okay. And it would be 4s2 and 4p4. Those are valence electrons. I'm using Lewis dot structures here at the same time. And then carbon, we did that one already. It has 2s2, 2p2, and has 4 dots around it. There it is. Okay. All right. So these are some generalizations we can make about valence electrons. Representative elements. Remember, first 2 columns on the left, the last 6 columns on the right are identified as representative elements. I don't know why they call them that. It's just so we'll agree on that name and go from there. The groups, if an element is in the same group as another one, they will have exactly the same valence electrons as other members of the group. So nitrogen, phosphorus, arsenic, we'll stop there because that keeps us in the nonmetals. They all have 5 valence electrons, the 5th position over, and they have a Roman numeral 5a. So that's one of the reasons that that old system was useful, because it told you how many valence electrons are there. The number of valence electrons for representative elements in the same, well, I ought to read ahead. Just what I just said. That Roman numeral tells you how many valence electrons there are. So the old system is useful in that respect. The new system is just arbitrary. Maximum number of valence electrons for any element is 8. Now, the maximum number for representative elements is 8. Once you get into the transition metals, then all bets are off. Okay. Okay, we did oxygen Lewis structure. There's the Lewis structure for oxygen. Okay, there you go. Phosphorus will have 5 dots around it. Come on. There you go. 1, 2, 3, 4, 5. Fluorine will have 7. So it's just missing 1. That's why fluorine, chlorine, they just want 1 electron. And they can get it either from a metal, transfer it, or they can share with some other element and make them think that they've got an extra one. All right, we're not creating electrons. When we share, yeah. No. I usually put, if we're going to form a bond using the Lewis structures, I usually put the single electrons on the side where it's going to bond with some other atom. That way you can show the sharing. Well, I'll give you an example in a minute. All right, so Lewis symbols or electronic dot structures have this is a shorthand method that we use. Now, it doesn't solve all the problems, but it is very useful for understanding some types of compounds. All right, we already said that. There's the octet rule. Okay. Now we go back to the ionic bond. We form ions by either gaining electrons or losing electrons. And the charge is based upon the balance between electrons after the transfer and the number of protons that are still in the nucleus. Remember, you can't touch the protons to make an ion. If you mess with the protons, you got a different element. So it's all the balance of protons with gain or loss of electrons. We got a name for negatively charged ions, anions. Positively charged are cations. Just memorize it. I could go into a long spiel about why we found those names, but I think in the interest of time, we'll just say, remember. Okay, I don't know how instructive this is. It just shows the formation of ions. It does make a good point of the fact that the chlorine atom, neutral chlorine atom, is smaller than the neutral sodium atom. But when we add that extra electron to chlorine, it balloons and the sodium shrinks because the size of the electron is the outer limits of the electron cloud. And that's really kind of nebulous. And it depends on what type of test you run, who you talk to, as to what size they are. But as a general rule, when you form an anion, it gets bigger. When you form a cation, shrinks. Okay. Chemical symbol for each of the following. Potassium atom loses 1 electron. So you just say K plus. If it loses 1 electron from a neutral atom, you're making it positive by 1 charge. Okay. Sulfur gains 2 electrons, right? And that makes sense. See where sulfur is under oxygen? If it's going to look like argon, it needs 2 more electrons. So you add 1 to get chlorine, add another 1 to get to argon. So you add 2 electrons to sulfur. Any of the chalcogens add 2 electrons, and you get a noble gas configuration. So sulfur would be 2 minus. We've added 2 electrons. Now, you need to remember those factors because when we start naming compounds, the first 2 types of compounds require that you balance charges. All right, we'll get to that today. So in an ionic compound, the alkali metals, the first column, they like to be +1. Second column, +2. Boron, aluminum, gallium, and indium, +3. Carbon is, it can go either way. It's a hermaphrodite. Then you work from the other side, fluorine and its group, the chalcogens like to be, not chalcogens, halogens like to be -1. And then oxygens and its group, the chalcogens like to be -2. The nitrogens, the nitrogen group, they like to be -3. And it's helpful to remember those facts in order to create the compounds, write the compounds out, and name them as well. So atoms can either lose or gain electrons, and the result in the formation of ions, cations, or anions. Any is possible. Just depends on whether they gain or lose. Okay. Atoms tend to gain or lose electrons until they have obtained a noble gas configuration. So this sodium, if it loses, notice with that 3s1 on the end, 2 possibilities. You can gain 7 electrons and look like argon. Right? Or you can lose 1 electron and look like neon. Energetically, which would be easier? Losing 1 electron. Right? So it loses an electron, and we back up to the period above. Over on the right, there's neon. Okay? So neon has 1s2, 2s2, 2p6 because that's the noble gas configuration. It's complete, maximum number of electrons. Okay. I already said that. All right. So I also mentioned this as well. The alkaline metals and alkaline earths are 1 and 2, respectively. Then the boron, aluminum, gallium, indium, they're +3. And that's when they're in ionic compounds. Believe it or not, well, you should believe it because we talked about it already. Some elements that are right next to that dividing line, sometimes they act like metals and sometimes they act like nonmetals, metalloids. So they can go either way depending on what other element they're interacting with. All right, I mentioned those already. The carbon group, its position is unique. It's halfway between the octet going one way and the octet going the other. So it really depends on the reacting partner, whether it loses electrons or gains electrons. If it's combined with a bona fide metal, then it usually forms a carbide where it's a negative charge. Okay. This concept, isoelectronic series, all that means is that when you consider ions, comparing ions of the different elements, you can create a group that has exactly the same electronic structure. And here's an example, right? Nitrogen, oxygen, fluorine, sodium, magnesium, and aluminum all have their ions all have the same electronic structure as, let's see, that would be neon. Okay. Now, they don't have to be, well, they usually are. Let me just put it that way. If you have an isoelectronic series, they usually can be referenced to a noble gas configuration. All right, we're going to skip this because we just don't have enough time. Those are all isoelectronic. And notice potassium is an alkaline metal, calcium is an alkaline earth, 2+. Argon is, let's see, yeah, argon is the result of losing 1 or 2 electrons respectively. And chlorine is to the left of argon. It gained electron. Now it looks like argon. Those all have the same electronic structure, and you can write that structure. Just look at argon and write its structure, and you've got all 4 of those. Oh, and here it is. Okay. Now, the number of electrons for each species would be the same because they're isoelectronic, 18. But the number of protons is going to be different because they're different elements. Okay. All right. The magnesium ion, if you look at the magnesium ion and you say, okay, if it's going to look like it's going to lose 2 electrons, be a Mg2+, it's going to look like neon. So all you have to do is pick the neon structure. There you go. That's its electronic structure. Okay. I mentioned this earlier. When we form an ionic compound, we actually transfer electrons from a nonmetal to a metal, from a metal to a nonmetal, excuse me, and form the positive and negative charges, and then we get electrostatic attraction. Now, if we use the Lewis symbols, this is what it would look like. Sodium has 1 valence electron because it's in the first group. It transfers that 1 electron over to chlorine. Now sodium is a plus ion, chlorine is a -1 ion, and we get the attraction. Similarly, oxygen needs 2 electrons. Oxygen is the nonmetal, sodium's the metal. 1 electron from each sodium goes to complete oxygen, makes oxygen look like neon, and makes sodium look like neon. And then you get the electrostatic attraction between the two, between oxygen and sodium. Similarly for calcium and chlorine. Okay, let's see. Ionic compounds are always neutral. There's no net charge. So you can use that when we start to build compounds. Go for neutrality. You know what their charges need to be, and you know that they need to be neutral, so you can adjust the numbers of each of the atoms so that you get neutrality. So when we write chemical formulas, we write the symbol, and the positive ion always comes first in the name. So sodium chloride. Sodium is a positive ion, a cation, and then the anion comes second. You don't have to write the charges. Sometimes I put the charges in just so that I can play with the balance, and then you can erase the charges afterwards. And if you need more, right, remember when you have a symbol, right, that's the number of them. When you need more of them, use a subscript. When you're building the compound. Okay, so if we're going to build a sodium phosphide, that would be the proper name. Sodium is +1 charge. Phosphorus is a pnictogen, so it's going to be a 3- charge. Right? It's 3 places to the left of the noble gases. That means 3 electrons are required to make it look like a noble gas. So phosphorus is going to have a 3- charge. And the ratio has to be 3 sodiums, one plus each, to balance that 1 phosphorus with a 3-. Okay, we come out neutral. Other possibilities. Barium is an alkaline earth, so it's going to have a 2+ charge. Chlorine is a halogen, a -1 charge. So how many chlorines do we need to balance? 2, right? 2 negatives balance 2 positives. So it'd be barium, BaCl2 would be the proper way to write that compound. When we have this one, when we know that iron has a 3+ charge and oxygen has a 2- charge, how do we balance that? Right? It's an odd and an even. The easiest way is to cross multiply. Right? Use a math trick. Bring that 2 over here, 3 over here, and just check it out. 2 times 3 plus, 6 plus. That balances a 6-. Okay? And that should pop up right there. The next one should be fairly easy. Lead 4+ and oxygen 2-. We need 2 oxygens. And you're balanced. It's all about balancing the charge with ionic compounds. Okay, the correct formula for aluminum chloride. We need 3 chlorines to balance that 1 aluminum. So there you go, AlCl3. All right. When an ionic compound is solid, like that crystal of sodium chloride, table salt, we have an array of positive and negative charges put together in such a way that they locally and for the whole crystal balance their charges. So that's a 3-dimensional representation on the right of what I was trying to put on the board in 2 dimensions. The sodium ions are going to be smaller. Remember, they lose an electron and shrink. chloride ions have acquired an electron, they got bigger. So that's why they look that way. Okay. For that reason, because the ratio of sodium to chlorine, sodium ions to chloride ions, is 1-to-1, that's why we write them like this. But they don't behave as a single unit like that, right? They have that big crystal. So depending on the size of the crystal, it could be sodium to the billion, chloride to the billion, right? Something like that, or even bigger. But that doesn't make any sense. It's more difficult to deal with. So we use, for ionic compounds, we use the simplest whole number ratio of ions, recognizing that the crystal structure can be huge. And rather than call that a molecule, we call it a formula unit. Okay. Smallest whole number ratio of ions. That's what we're trying to show here. So the terms that we use are the formula unit. Check. Okay. I mentioned the alkaline metals, alkaline earths, the boron, aluminum, gallium, indium group. But there are some transition metals that have fixed charges when they're in ionic compounds. The alkaline metals, alkaline earths, and the aluminum group, boron aluminum group, they definitely have fixed charges. But there are 3 transition metals that also have fixed charges. Start with zinc on the far right of the transitions, right? It's a 2+. Below it, cadmium is a 2+, always in ionic compounds. And then to the left of cadmium is silver. It's always a 1+. The rest of the transition metals can have multiple charges. That's important to recognize when we start to write, to build compounds. Those are fixed metal charges. Okay, all right. So now we're going to build and name compounds. And we're going to start with binary compounds. Binary ionic compounds, as a matter of fact, and then we'll transition to binary covalent compounds. Now, the next chapter, chapter 5, focuses on covalent compounds, but it makes more sense if I give you the rules all together, both ionic and covalent. So that's what I'm going to do in this chapter. And then we'll advance to more information about covalence in the next chapter. All right. Type 1 compounds. These are between metals and nonmetals. And the distinguishing characteristic here is that the metals have a fixed charge. Right? So the metals would have to be alkali metals, alkaline earths, boron aluminum group, or those zinc, cadmium, silver. They would have to be those metals only. Okay. And because the charge is fixed, it's easy to balance the charges because we know what the metal is. Right. This system was set up by IUPAC, International Union of Pure and Applied Chemists. They have a subcommittee that does nothing but figure out how to name compounds. Okay. And they came up with this system, the type 1 compounds, and the overriding, there are 2 rules that override, if I can remember what they are. Let's see, one is the name must be unambiguous. That is, when you name a compound, you can write the compound and it cannot be anything but that formula for the compound, right? There's no two ways about it. You either write it right or you write it wrong, okay? And no redundancy, non-redundant. And that'll become apparent when we get to type 2 compounds. I'm going to leave that one till then. So if the metals are a fixed charge, then all we have to do is say, what's the metal name? Remember, the cation comes first. So we'll use sodium chloride. We know that that's a +1 charge. And the chloride then would have to be a -1 charge to balance it. And in fact, all the halogens are -1. So we name it sodium. We just say the metal, just say the element name, and then we change the ending for the chlorine to IDE. Okay, sodium chloride. That's the name of that compound. You don't have to add anything to it. We don't have to say that sodium is a 1+ charge somehow, right? Because it's fixed, right? That would be redundant. Let's try something else. Well, let's see. We probably got examples. Well, there are some of the elements. The IDE ending is common across all the anion positions. So bromine would be bromide. If carbon were an anion, it would be carbide. Chlorine, we did that one already. Fluorine is fluoride. If hydrogen is in this position, it's hydride. Iodide, nitride, oxide, phosphide, sulfide, those examples. Oh, yeah, good. We got some examples here. So KCl is potassium chloride. And we know that we write it this way. And the whole point of this system is that you can go both directions. If you're given a word problem with the name of a compound, you'll be able to write the compound formula. And you have to be able to do that. Otherwise, you can't proceed to the next step. See, we've learned the alphabet, the element symbols. Now we're learning how to construct words. Then we're going to go to chemical reactions, how to write those out. That's like writing a sentence. But we got to master each step before we can move to the next one without making mistakes. So potassium chloride, potassium is an alkali metal. It's always a +1 charge. Chloride is a halogen. It's always a -1 charge when it's in ionic compounds. That's the kicker. If you form chlorine and some other nonmetal, then it's a different rule. But as long as it's with a metal, then it's a -1 charge. And if you look at your periodic table, you'll see, especially the nonmetals, you'll see a list of charges, looks like charges, down one side of the square. The top one will be the ionic form. And the others are what we call oxidation states, and we haven't got there yet. So don't worry about that right now. Magnesium bromide, is that one written correctly? Right? With a -1 charge and a 2+, yeah, 2 times the -1 is a -2, balances a 2+. And calcium oxide, calcium is always 2+. Chalcogens, oxygen, is 2-. So you only need one of them, one of them each, right? Simplest whole number ratio for ionic compounds. That's a type 1 compound. It's the simplest one to name. That's why we started with it first. Type 2. Type 2 compounds are also metal and nonmetal. But in this case, the metal has the potential for different charges. Now, it doesn't change charge. Once it's in the compound, it doesn't change its charge, but it has the potential to be different charges as it goes into the compound. Iron is a perfect example. Iron could be a 2+ or a 3+. Right? And all of the transition metals and some of the metals over there underneath the non-metals have the potential for multiple charges. The only ones that don't are zinc, cadmium, and silver. The rest of them have multiple charge capabilities. That being the case, when we write the compound, we have to say what is the charge. Okay? And we use a Roman numeral for that purpose. So if we say that we're going to form an oxide with this iron right here, then if we do that and form an oxide, which is 2-, we only need one of each. But to name it, we have to say iron, and we borrow from this convention, iron oxide, but we have to say what the charge is. Iron 2 oxide. That's a change that happened after I left my undergraduate career. Before, we had this antiquated system. This would be ferrous oxide. This would be ferric oxide. So they've made it a lot friendlier. So now you just say iron 2 oxide. That's it. The problem with ferrous and ferric and the other us's and ics is that it depends on which element it is as to whether the charge is that or something else. So it was really messy. Okay, iron 2 sulfide. Sulfide is in the chalcogen group, so it's a 2- charge. So you just substitute sulfur there and sulfide here, and you got the name. PbO2. Now, sometimes you have to deduce what the charge is. If you're given the formula, like PbO2, you know that oxygen is 2-. So that's a -4 total. That means this one iron has to balance that. So now we know it's iron 4 oxide. Okay? Those are type 2 compounds. We make them unambiguous by saying what the charge is on the metal. See, before we get to that, so if we went back over here, speaking of this second rule, non-redundancy, if we had this one and we said sodium 1 chloride, that would be wrong. We don't have to say that because we know sodium is always +1. That would be redundant. That's why we leave it out. Okay. All right. So what I've got here, and there should be a copy of this in your review document, probably in the back pages. But check it to be sure. Because if it's not, I need to get you a copy. It's a review document. Here it goes. Periodic table. Yeah, there it is right there. So there's a list of polyatomic ions. Okay. Another fly in the ointment. What do polyatomic ions do? Polyatomics are just that. They're several atoms bound together. In fact, they're bound by covalent bonds. So they behave as a single unit. So for instance, if we have NO3- is a polyatomic ion. And you'll notice the list on the left is a duplicate of the list on the right. It's just the one on the left is arranged alphabetical by the name, and the one on the right is alphabetical by the formula. Right. So just use whatever size you need. They're duplicated. So if we look on the left, go down to nitrate, it's NO3 minus. There we go. So if you read a compound that says nitrate in it, you know to go and put NO3 with a -1 charge in order to balance the charges. But these act as a single unit, and that negative doesn't belong to an oxygen. It belongs to the whole group. Okay, it's spread over the whole group. So if you need more than one of them, then you can't change the subscripts. You have to use a parentheses and just however many you need. All right. So that being said, all of these polyatomic ions that were given you in the list are negative except for one. So these are all going to be in the anion position, the second position, except for ammonium. Okay. So everybody knows about ammonium nitrate, right? Ammonium nitrate plus 6% fuel oil plus a blasting cap makes a really fine bomb. Just ask, well, you can't ask Timothy McVeigh now. He's been executed for blowing up the Alfred P. Murrah building in Oklahoma City. That's what he used. Big barrels, ammonium nitrate, fuel oil. I don't know whether he stuck a blasting cap, probably stuck a stick of dynamite in there with him. That's a sticky subject. Anyway, so you can use these polyatomic ions can fit in either this one or that one. Right? If you use this one cation, it would go over here because it's a fixed charge. And you don't have to change the name, it's just ammonium. That's it. The polyatomic ions have their names and you don't change them. All the others would go in this position, so it depends on the metal as whether they're type 1 or type 2. Okay, so I know that's kind of small, but I wanted to get everything on one page. So here are examples of compounds with polyatomics. The first two have the anions, polyatomic, and the last one has both cation and anion. All right. So for sodium hydroxide, sodium is +1, and you look up hydroxide, it's got a -1 charge. So it only takes one sodium and one hydroxide. That's it. And that would be a type 1 because sodium is a fixed charge. Okay. Now, a mistake that some students make is they'll take the hydrogen and they'll say sodium hydride. That's not that compound. OH is hydroxide. Hydride would be that. Okay. Magnesium nitrate. Magnesium is a 2+ charge. We're still a type 1 compound because it's an alkaline earth. And nitrate, which is a -1 charge. So magnesium being a 2+, that N now becomes 2 to balance the charge. 2 minuses, 2+. And ammonium sulfate, ammonium is a +1 charge. Look up sulfate, it's a 2- charge. So we need 2 ammoniums. That's why the parentheses. Now, the question that may be rattling around in your brain is, how do you know when you've got a polyatomic ion? If you don't memorize all of them, there are clues. Usually, the anions will have an oxygen in them. Not all of them, but most of them do have an oxygen. So if you have 3 elements or more in your formula, and there's an oxygen there, suspect polyatomics and at least look for them in the table. Examples of polyatomics that don't have, here's one that I can think of. I think that's a -1 charge. The cyanide ion, right? Murderer's best friend. Well, I don't know, acquaintance, perhaps. So if we had sodium cyanide, it would just be this. Right? A friend of mine was a lepidopterist. You know what a lepidopterist is? They collect butterflies and moths. He had a huge collection. These display drawers that he'd bring to work sometimes. And he had a kill jar. And what he did was he put sodium cyanide or potassium cyanide crystals in the bottom of it. And then he put like a gauze or something over it. And then he filled it with a thin layer of plaster of Paris. Right? And then he just put the insect down in that jar and closed it. And gradually that cyanide would sift through, would permeate and kill the insect. And then he'd mount them. Let's see. All right, now on to type 3s. So the polyatomics are useful for type 1s and type 2s, but not type 3s because they are ions. The type 3s are composed of nonmetals, two nonmetals. We're still talking about binary compounds. Now, these are not ionic, they're covalent, but we're going to borrow from the type 1, type 2 and make slight changes for the type 3s. You want to put one of the elements in a position that would be the cation position and one of in the anion position. And as a general rule, knowing which one to put first is the one furthest to the left, closest to the metals, you would put first. So for carbon dioxide, carbon is closer on the left to the metals than oxygen is, so carbon would come first. And since they don't have a charge, we actually have to say how many atoms are in the formula. Right? And these are molecules. They're not just formula units. They are molecules. They act independently. So you have a cation position and then the anion position, but they're not ions. And you simply say how many of each. And you need your prefixes. I think they're on the next page. Yeah. These are the Greek prefixes. They go way up higher than 10, right? But this will be enough for us, right? Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Those are the 10 prefixes. So if we have this formula, right, that we look to see, are they nonmetals? Yeah, both of them are nonmetals. So we know we name them with the type 2 convention. One rule, though, is we don't say mono. For some reason, it just doesn't sound right for the first one. So we just say carbon. If there are 2 carbons for a different formula, if there were 2, then we would say di. But we don't say mono for the first one. We do say mono for the second one if it's true. But in this case, we have 2. So we simply say di, and we borrow the convention by changing the ending to IDE. So carbon dioxide is that. So how would we name this one? Let's say dihydrogen monoxide. That's water, of course. Some compounds have grandfathered in names. We don't name it that. That's water. Okay. So there's carbon dioxide. Now, if you have just one, say like this, and that, now you get the really deadly one. Carbon monoxide. That's the one that you don't want to breathe too much of it. Okay. Does anybody know how carbon monoxide works? How it kills? Well, if you had red blood cells, right, you've got hemoglobin on all your blood cells, and each hemoglobin molecule can hold like 4 oxygen atoms. Carry those oxygen atoms to the cells and dump them off. Well, if carbon monoxide is present, it binds in the heme structure with where the iron is. Like there are 4 iron molecules in every hemoglobin. Carbon monoxide binds with the iron almost irreversibly, much stronger than oxygen does. So it binds to the hemoglobin and competitively inhibits oxygen binding. So you essentially suffocate at the molecular level with carbon monoxide. Okay, enough of that. So if we have SF6, we say sulfur hexafluoride. Or if we say this one, dinitrogen tetroxide, we know that it has oxygen in it and it has nitrogen in it. And we know that those are both nonmetals. And we know that we need 2 of these and 4 of those. So that's how we would write it. Right? It's both unambiguous and non-redundant. Okay, type 1, 2, 3. So if you're presented with a problem where you have to name a compound, you look to see, is it non-metal, or metal? If it's non-metal, you automatically go to type 3 to name it. If it's got a metal in there, you say, all right, which one is it, type 1 or 2? And you look for fixed charge elements, like the alkaline metals, alkaline earths, boron, aluminum, gallium, indium, or zinc, cadmium, silver. So AgCl would be silver chloride. That's it. That's all you have to say, because it's a fixed charge, type 1 compound. And there's a flow chart if you like to use them. Helps you with your decisioning. Why do I need that one? Oh, polyatomics. Right? And the polyatomics, they look like they complicate the situation, but they really don't if you follow the rules. All right. Now we go from sublime to ridiculous. Naming acids. The nomenclature for acids, a type of nomenclature already existed from the alchemists through the Middle Ages. So the IUPAC committee had to come up with a compromise. How do we incorporate those names that were in common use by the time modern chemistry started getting rolling? How do we accommodate those names and make it systematic? So we've got some rules that we go by. Now, if you have a compound, say HCl, if we name that here, hydrogen is a fixed charge. It's first, so it's going to be a +1 and a -1. So we name it like the type 1 convention. We say hydrogen chloride. And hydrogen chloride is a gas. Okay. But if you dissolve it in water, now we have to change and use the acid naming conventions. Okay. And these are the rules. acids will have at least one, sometimes more, hydrogens at the beginning of the name. So this one has one hydrogen. One with a polyatomic like this one has two, right? The hydrogens would assume a positive one charge, and the sulfate, being a polyatomic ion, needs two of those to balance it. Okay? So that's one clue. The other clue is it has to be an aqueous solution. Right? If it's not, we would say dihydrogen sulfate. But aqueous solution, we use the acid naming convention. So we look for the hydrogens first, and then is it in solution? Then we look for the presence or absence of oxygen in the molecule. Right? This one has no oxygen in it. So to name it as an acid, once it's in solution, we start the name with hydro. That's only if there's no oxygen there. And then we take the chloride, and ides become X. So it's hydrochloric acid. Okay? If it has an oxygen in it, we don't say hydro. We drop the hydro, and we go straight to the non-hydrogen part of the molecule. So eights become X in this case. We simply say sulfuric acid, like that. Sulfic doesn't sound right, so we call it sulfuric. Now, we pay attention to aesthetics sometimes in chemistry. If we have this one, like that, in aqueous solution, now we start with hydro. This one is hydrosulfuric acid. Okay? It's all based on that oxygen. Is it there? Is it not there? And other examples. Nitrate, hydrogen nitrate becomes nitric acid. Sulfuric acid. C2H3O2 is a polyatomic ion with a -1 charge. Acetate becomes acetic acid, right? And if you had salad dressing on your salad, you probably had some acetic acid in it. 5% acetic acid is vinegar. It's a weak acid, right? So it's not going to eat out your mouth, rip your lining off your mouth, or mess up your stomach. In fact, acetic acid has a buffering ability, and some people drink it, right? Warm acetic acid every night, warm vinegar every night. Swear by it. Okay, so eights become X. Ites become us. So if it's NO3, HNO3, that would be nitric acid. If it's HNO2, right, that's a -1, this is a -1. This is nitrate, this is nitrite. The ites become us's, so it's nitrous acid. Okay? Similarly over here, if we have H2SO3, that's sulfurous acid. Okay? That's what we're trying to show here. Let's see. Before we get to that one, let's go back to the polyatomics for just a second. I know that list looks huge and scary, but some of those polyatomics have patterns to them. And one example is the chlorine oxygen group. if you have ClO3 minus, that's the chlorate polyatomic ion. You take one oxygen away, it still has a -1 charge. That's chlorite. Now, if you take another one away, we don't have any more suffixes that'll work, so we have to put a prefix in also. We say hypochlorite, underneath the chloride, like hypodermic, underneath the skin. Hypochlorite, polyatomic ion. Then we can add one more oxygen. And this is perchlorate. Okay? I looked up per the other day. Per is a prefix that means perfect. So it's got the most oxygens we can have. So there's a family, like a sequence, a homologous sequence. And you can do this with all the halogens. Well, except for fluorine. You can use bromine in here, perbromate, bromate, bromite, hypobromite. You can use iodine, periodate, iodate, iodite, hypoiodite. So with just that sequence, you got what? 12 polyatomic ions, just like that. There are other multiples, but this is the biggest one. Okay, now to make acids out of these, all you have to do is add a hydrogen. And then you take the name, since it's oxygen is present, we don't say hydro. We just take this name and this becomes, eights become X. So this is perchloric acid. And of course, these have to be in aqueous solution. 8 becomes X. This is chloric acid. Chlorites become us's. Chlorous acid. And hypochlorous acid. So there you go. Now you got 12 more acids memorized. This one is very useful. Extremely strong acid. Strong oxidizing acid, which doesn't mean anything. But we used to use it when we were digesting plant material. Right? You want to get at the ash, the mineral components of a plant sample. So what we didn't do was put concentrated perchloric acid, which is, I think, 70% by mass, in with an organic material. If you do and heat it up, you're likely to get an explosion. So if you want to cause havoc, just take perchloric acid in a tall beaker and drop a nice big pat of butter in it. Put it on your hot plate, turn the hot plate on high, pull the sash down and evacuate the building, because it will blow. So to get around that, we did a pre-digestion. We had all our samples set up, weighed out in the beakers, and we put nitric acid on them, cold nitric. Actually, I'm not sure if that's right. I know nitric acid is 70% that we used. We put cold nitric acid on them, put them under the hood, and just let them sit overnight. And they would do a pre-digestion. Then we would add perchloric acid, heat it up. It's just as safe as it could be. Okay. That's what I wanted to say about patterns in the polyatomics. Then if we look at these following compounds named incorrectly, right? Potassium and nitrate ions. Type 1, type 2, type 3. Type 1, right? Metal, potassium is a fixed charge. So we name it potassium nitrate. Ti, titanium and oxide. Right? Titanium is a transition metal, and it's not zinc, cadmium, silver, so it's possibility of multiple charge. So we look at TiO2 and say, okay, oxygen is a 2- charge times 2 is a -4. So we have to balance the titanium with a +4, right? Wrong. It says titanium 2. That's wrong. It needs to be titanium 4 oxide. So that's wrong. Hydroxides are all -1. And if we have 4 hydroxides, that means 10 has to be a +4 to balance those 4 minuses. And 10,4 hydroxide is correct. 10 is not a transition metal, but it's over underneath. See the SN? It has multiple charges available. 10,4 hydroxide. And then PBr5, 2 nonmetals. Right? So we use the type 3 convention, phosphorus, pentabromide. Okay. How about the other one? Calcium and CrO4. All right, we got 3 elements there, and one of them is oxygen, probably a polyatomic ion. You look it up, and it turns out to be chromate. Chromate has a 2- charge, you see from your table. And like I've said before, that review document has the polyatomic table in it. That means the exam will also have it. Okay, so you don't have to memorize all of them. If you use them enough, you'll memorize a few of them anyway. So calcium is 2+, chromate is 2-. We just need 1 of each. So TiO2 is the only one that's misnamed. All right. I think I mentioned this before. Those polyatomic groups are covalently bound atoms. So they're always 2 nonmetals, 2 or more nonmetals together. There'll be 3 in C2H3O2, be the acetate. They're all nonmetals. They're covalently bound very tightly into that unit, that charged unit. That's why they behave as single units. I mentioned this before. Let's see. Oh, there's a typo. NH4+. Ammonium is NH4 down here and plus up there. That's a typo. Okay. And the hydronium ion is one that we'll talk about when we talk about bona fide acid-base reactions. Then we'll get into the hydronium. But it is a polyatomic ion. It's just we don't find it in compounds. We find it off by itself, doing its own thing. Okay, let's see. Let's skip that. All right. And I mentioned this already. You cannot modify a polyatomic ion. In other words, the charge on the polyatomic is shared by all the atoms. So if you want more than 1, you have to use the parentheses. It doesn't happen too often. Most students get that pretty quick and don't try to change it, but every once in a while, I get a student that wants to change the subscripts. Okay, well, let's go. That one's already been done. I don't know why I got that slide in there twice. Ammonium carbonate, right? There you have 2 polyatomics. Carbonate, CO3 with a 2- charge, ammonium with an NH4 plus 1 charge. You need 2 ammoniums. So we'll have a subscript with 2 ammoniums and 1 carbonate, which is C. Now, where do you see carbonate? Yeah, actually in the grocery store. No ideas? Nobody reads labels. I read labels all the time. Well, you can see it in several places. You can see it in soda pop, carbonated beverage. It has CO3. Or you can see it, actually, you don't see the carbonate. Baking soda. Baking soda is actually a different polyatomic ion. Instead of CO3, baking soda is that hydrogen carbonate. And then you have a sodium on the front of it. Sodium hydrogen carbonate is baking soda. The old name for it is sodium bicarbonate. Bi is a prefix that means hydrogen. So that's the old name, and I'll probably get that from several of you if it shows up in that extra credit where you name things. And I figure that if a student does that, they've just gone to the internet and looked it up. They're not trying to figure out how to write the names. They're just, looking up the names so they can get credit. You can do that, but it's not going to do you any good on a test or in the future for that matter. Learn how to do it on your own, and the benefits will be lasting. Okay, I know this is the last slide. It's not covered in your book, I don't think. But what do you do for waters of hydration? Well, first of all, what is a water of hydration? You name the ionic compound. It's either a 1 or a 2. Waters of hydration don't work with type 3s, only 1s and 2s. So you write the compound, the ionic compound, and then you attach water to it. Waters of hydration are crystal structures for your ionic compounds that have within them water molecules left behind. We know they're there because if you dry say you have calcium sulfate in solution, and you dry it down at say 105 degrees Celsius, just enough to boil off water, right? Just above the boiling point of water. What you'll get is a compound that still has a little water left in it. That's part of the solid crystal structure. And the only way you know that you can get it out of there is heat it higher. 150, 200 degrees should do it. And we know that the mass decreases when you do that. And we can determine, I don't think we have one of those experiments. I do it from a general chemistry class. We can determine that you have actually 2 water molecules for every 1 formula unit. You have 2 water molecules in that crystal structure somewhere. And the way you identify that as water of hydration is you put that dot in the middle of a line, not on the bottom of the line. That's a period or a decimal point. You put it in the middle of the line, and that designates waters of hydration. Right? You simply name the compound, and then we would say calcium sulfate, correct? Calcium sulfate, dihydrate. So the water's name becomes hydrate, and you just say how many there are. Okay. Here's another example, zinc sulfate. When you do the same thing to a solution of zinc sulfate, you end up with 7 waters, zinc sulfate. Everybody knows Epsom salts, right? They're good for strained muscles or for constipation, or it's the other way around, diarrhea. No, it's a laxative, right? Epsom salt. When you do the same thing to Epsom salt, that's magnesium sulfate with 7 waters. Heptahydrate. Am I out of time? I see people packing up. No, we go to 1 o'clock. Or do you have to leave? Somebody have to leave? Or are you just trying to stay awake by packing things? I can relate to that. I had to pop a caffeine pill on the way in this morning. Sleep deprivation. Okay, so that's the way we name compounds with waters of hydration. And concept questions, we could do them. But there's the answer. If you're so inclined, check it out. And there's a second one. Fill in the following table. Oh, all right. We can do that. We did that one already. I erased it. Sodium hydrogen carbonate. Hydrogen carbonate is a polyatomic ion. Let's see. Sodium phosphate. Write the formula for sodium phosphate. Which is the type 1, type 2. It's a metal and a polyatomic, so it has to be one of these. Sodium is a fixed charge, right? So it's type 1. So we have sodium, and then you look up your phosphate. It has a 3- charge. So we need 3 sodiums. Okay. And then magnesium hydrogen carbonate. Hydrogen carbonate is a -1 charge. So, and magnesium is a fixed charge, so it's still type 1. Magnesium hydrogen phosphate, and that's all you have to say. You don't have to say how many hydrogen carbonates there are, because we can deduce that from their charges. And then magnesium phosphate, EMG, let's do that one. EMG is an alkali metal with a 2+ charge. Phosphate is still 3-. So how do we do that one? Remember? Right. Bring the 3 over here, and the 2 comes over here, like that. We're good to go. So let's see which one satisfies. B. And that's it for chapter 4.